お、すごい音。
絶対水フィルターかってるんですかね。
Good God. Whole 10 years I've been here, I ain't never saw this running this fast.
¡Liberado el río! Ya Dani.
trying to avoid me now at some point.
It was an unprecedented show of force at Roosevelt Dam when all 4 spill gates were opened, releasing 105,000 gallons of water per second.
Oh yeah. Oh yeah, that would be awesome.
It's a giver and taker of life. With it, barren land can be cultivated. Without it, no life can be sustained. Because human history is replete with cycles of drought and flood, we have sought both to conserve and to protect ourselves from this destructive yet essential resource.
If you're going to develop the resources of a nation, you want to not let the river just flow into the sea without making some use of it.
And we maximize our water use with dams. There are an estimated 900,000 dams worldwide. Most are small to medium-sized. But 40,000 are over 50 feet high. The most familiar dams, the mega dams. A select club of about 300 over 450 feet high, are vital pieces of civilization's infrastructure.
In the 1930s, we in the U.S. realized that we could manage entire river basins, not just one single dam at a time, but dozens. So we began developing river basins on a vast scale.
It is scale that makes dams unique. In the 1930s, dams in the United States became the largest constructions on Earth, and more than just huge feats of engineering.
They were seen as monuments, as symbols of progress. We're using more material than has ever been used before since the time of the pyramids. And that's something that you celebrate.
Grand Coulee Dam is the largest concrete structure in the United States. Other giants include Hoover Dam and Oroville Dam. But they are not new. And because of environmental opposition and the lack of new sites on America's waterways, no dams this size will be built again in the United States.
We have essentially built as many as we need or is feasible to build. Dams do not create water. There has to be water that can be manipulated through them to make them viable. In America, we have done that.
But when the U.S. was building big dams, the developing world was taking note, and with increasing regularity has followed suit. Aswan Dam in Egypt, Itaipu Dam between Brazil and Paraguay, and finally, the most ambitious hydroelectric dam in the world, China's Three Gorges Dam, which will exceed all other dams in size and power production. Like any hydroelectric facility, Three Gorges Dam will harness the power of water released from an elevated reservoir to drive turbines and produce electricity. This process is standard. What's unusual is how much electricity it will produce.
The hydroelectric generators that are attached to this dam will generate 18 million kilowatts of power, an enormous amount of power, the equivalent of 18 nuclear plants.
That's enough electricity to light up Shanghai, China's most populous city of almost 10 million people. Construction on the Three Gorges Dam began in 1994 with the digging of a canal to reroute the Yangtze River. Earthen dams diverted the river's flow around the construction site.
In the case of the Yangtze River, it's the third largest river in the world. It needs to be completely diverted for a period of over 10 years while the dam is being built.
Holding back the flood-prone Yangtze River has long been a top priority for the Chinese. Over the last 2 millennia, the Yangtze River has averaged a major flood once every 10 years. But in 1918, it wasn't flood control, but hydroelectricity that compelled China's revolutionary leader Sun Yat-sen to promote a Three Gorges Dam project. The country's instability sidelined the project until floods in the 1930s and 1950s killed hundreds of thousands of Chinese, spurring Chinese officials to begin planning in earnest for a dam with a massive reservoir that could reduce flooding and produce electricity. Because of the enormity of the project, the dam remained in the planning stages until the People's Congress approved it in 1992. Plans called for a 607-foot-high, 1.4-mile-long concrete gravity dam with 2 powerhouses flanking a central spillway, capable of passing 3.5 million cubic feet per second of the river's water. Three Gorges Dam would contain 35 million cubic yards of concrete, enough to lay a 16-foot wide highway across the U.S., more than 10 times. In 1997, with the diversion canal keeping the site dry, workers began pouring concrete.
In a dam, you start by creating what's called lifts of 2 to 3 to 4 meters, where forms are put on the side to keep the concrete in a certain designated area. Then concrete's poured in that area.
After pouring concrete for 10 years, workers finished the main structure of the dam in 2006. An estimated 250,000 people have worked on this $22.5 billion project, the costliest and perhaps largest construction project in modern history.
Many times, big projects in developing countries are built by large American or European companies. But the Chinese decided they wanted to build this mostly on their own, with help in specialized areas from Western engineering companies.
With the dam structure complete, the river was returned to its natural course and impounded in the 400-mile-long reservoir behind the dam, inundating 13 cities, 140 towns, and almost 1,400 villages. The most dramatic chapter in an ongoing relocation of an estimated 1.4 million people. Some experts predict that relocation costs will equal the cost of the dam itself. Adding to the controversy surrounding the dam is the fact that its reservoir will flood countless sites of historical and archaeological importance and inundate some of the area's most fertile farmland. But when the 26 4-ton turbines are in place and generating electricity, they will supply 3% of China's power needs. The Chinese are still installing the generators, with full power production expected in 2009, 1 year ahead of schedule. Dams may be the construction giants of the 20th and now 21st centuries, but their impact on civilization is ancient. 5,000 years ago, Mesopotamians developed this new technology, the dam, to transform the desert into what would be known as the Fertile Crescent. Mesopotamians used embankment dams, earthen and stone structures that hold back water with their mass to divert water into irrigation canals that fed their fields. As dam technology spread throughout the region, the dams themselves began to grow. Civilizations attempted to store water in reservoirs, not just divert it.
Diversion dams are the earliest, but you don't store a lot. You're still dependent upon the natural flow of the river. As dams get taller, you have the capacity to actually store the water, to capture those spring floods, those freshets, and then use it later in the year.
But holding back a reservoir with just the weight of earth and rocks takes massive amounts of material. The Romans engineered a way to do more with less.
If you took a masonry wall and didn't build it straight across a canyon, but you built it with an arch, that you could actually use the strength of the arch to help hold back the water.
But the arch is only as strong as the foundation into which it's anchored. Arches were suited to narrow areas with solid rock foundations. The next innovation, buttress dams, were more versatile. They spread their load across a series of buttresses, didn't require massive amounts of fill material, and could span wider areas. Despite these innovations, the most common dam is still the earthen embankment dam. It's the dam of choice in areas where the dam site is wide, and there are large amounts of earthfill available. An embankment dam is the tallest in the United States. The 770-foot-tall Oroville Dam on the Feather River in Northern California was built in the 1960s from clay and cobblestone, recycled from an abandoned gold mine.
The clay is actually from a clay pit just a couple miles away from here. It was brought up to this location via a train system.
By 1963, workers had diverted the river with 2 tunnels and cleared the site to bedrock. Next, they began placing earthfill. Oroville Dam is a gravity dam that holds back water with its mass. The core is composed of impermeable clay, surrounded by a transition layer of coarser material, and covered in rock, sand, and gravel. The weight of the structure is simply too great for the reservoir to push aside. During construction, bucket wheel excavators dug out 3,500 cubic yards of fill per hour. Workers transported the fill on conveyor belts to the train hopper, where they loaded 40 train cars every 15 minutes. 3 locomotives continually carted the 80 million cubic yards of earth material to the site where workers sorted it, dumped it into the dam, and packed it down. Completed in 7 years, the Oroville Dam supplies electricity, drinking water, and irrigation for Central and Southern California. Its reservoir and spillway also provide flood control.
What the spillway provides for us is a safety device if we need to release water out of the reservoir and get it around the dam into the Feather River.
When open, 8 30-foot-tall gates are capable of releasing 250,000 cubic feet of water per second to the river below. Oroville, the 19th largest dam in the world, dwarfs most dams in the U.S. Still, engineers are retrofitting many smaller water storage and irrigation dams with hydropower, finding ways to make more electricity from lesser dams. In the 20th century, dam building displaced as many as 80 million people worldwide. Dams will return on Modern Marvels. At Rock Island Dam on the Columbia River in the heart of Washington State, a test of strength is taking place. No, it's not dam versus river. This facility has withstood the water's pressure for more than 70 years. But today, deep within Powerhouse 1, a decade-long modernization is about to begin, and it starts with a deadlift. Workers will have to hoist the rotor, a 271,000-pound steel and copper assembly, out of the top of the generating unit. In each one of these 10 power units, the rotor, a rotating electromagnet, spins inside a stationary stator, which is packed with conductive copper wiring. The rotor's spinning electromagnet carries a charge that causes electrons to move from atom to atom in the stator's wiring, producing the electron flow called electricity.
There's a huge magnetic force of about 1 million pounds that tries to draw these two magnets together. So engineers work to design systems that can keep that rotor spinning at up to 90 RPMs perfectly inside the stator.
As the equipment ages and bearings wear down, the rotor begins to wobble and runs the risk of banging into the stator, potentially destroying the machine. So it must be pulled out and upgraded. An operator positions 2 bridge cranes, each capable of hoisting 80 tons above the rotor. This is delicate work. The rotor must be perfectly level as it's coming out.
There's about 1/8 of an inch gap between the rotor and the stator. And as they've been lifting the rotor up, because it's not level, it's been coming in contact and hanging up on the edge of the stator.
Finally, the crane operator levels the huge rotor enough to extract it. The cranes cart the load the length of the powerhouse and gingerly set it down.
This unit was originally installed in about 1953, and this is the first time it's been out. So it's been in service for well over 50 years.
Over the years, insulation and copper windings have worn down from exposure to heat, vibration, moisture, and oil. Wear and tear decrease efficiency and can shut the generator down.
The rotor will sit there for about 4 months while work crews remove the old copper laminations and install new copper laminations of improved purity and design.
The Rock Island modernization will take 10 years and cost $180 million. The project will extend the life of the powerhouse another 50 years. After the upgrade, the dam's power plant will produce 10% more energy from the same amount of water. This idea, using dams to generate electricity, began at the end of the 19th century with the advent of power lines that distributed electricity over distances. Private utilities began to build hydroelectric dams, even in remote areas.
The coming of hydroelectricity and the coming of electric power systems in the 1880s and the 1890s really has a huge impact on why people want to begin to build dams in many, many different locations.
Over the next 100 years, states and industries hungry for water and power began damming up virtually every major river in the United States. In the 1930s, President Roosevelt, in an effort to stimulate the depressed economy, authorized the building of some of the country's largest dam projects, including the Shasta, Bonneville, and Grand Coulee dams. Decade by decade, over the next 40 years, the number of dams built would skyrocket. 1,400 dams built in the 1930s would spike to 8,000 built in the 1970s. Many of the smaller dams were designed for water storage and irrigation, not hydropower. Today, the high cost of electricity has spurred interest in adding hydropower to these smaller dams.
They tend to be low head. That means the difference in elevation from the upstream to the downstream of the dam is not so high. And these were not so economical to develop and to extract power from these dams, which were often there for water storage or for navigation. But today there is an interest in developing special designs for these low-head dams.
Every project for Voith Siemens, a 140-year-old German company with a hydropower design facility and manufacturing plant in York, Pennsylvania, calls for custom design.
Each project has a unique height of the dam, a unique amount of water versus the time of the year. And so to match each of those variable conditions, each plant is designed exactly for its condition.
The lower head dams on the Mississippi and Ohio rivers require a compact power plant. There isn't much depth at these dams. As a result, axial flow bulb turbines have been designed to be installed horizontally, with the turbine and generator all packed into one compact unit.
It basically has a central hub with the blades welded to the hub. This whole runner is also made 100% of stainless steel. This design will go into a powerhouse structure that has a lot of water flow but very small head.
At dams with higher head, in the 75 to 1,200 foot range, engineers employ a Francis turbine. These turbines have fixed blades welded at the top and bottom to a crown and a base. Francis turbines have greater structural rigidity to withstand increased water pressures at these higher head dams.
The water actually comes in and makes contact directly with this surface of the bucket. Kind of like a prize fighter. When he hits his opponent, he wants to hit his opponent squarely. If he hits his opponent at a glancing blow, he doesn't transfer that energy. The water operates on the same principle with these buckets. The water conveyance system would involve the penstock, delivering the water into a spiral case. And a spiral case looks like a snail shell, where it's bigger at the opening and it volutes into a smaller diameter as it wraps around the machine.
This accelerates the water into the Francis runner, which weighs 56,000 pounds, spins anywhere from 150 to 250 RPM, and must be perfectly balanced. A giant lathe slowly shaves it down.
We remove metal in designated areas on the runner so that the runner is balanced.
These massive turbines cost up to $10 million to manufacture, and as much as $1 million just to ship to the dam site where they will be installed. But energy from hydropower is extremely valuable because water power is flexible.
One of the great advantages of hydro is you can turn it on and off relatively quickly. If you have a big coal-fired steam plant and you get that baby going, you can't turn that off very easily. It might take days to cool down, and it's going to take days to heat back up. With hydropower, you can actually turn those valves and in a matter of minutes go from nothing up to full power. And that's its great advantage.
But when these hydroelectric barriers block once free-flowing rivers, how can ships and fish get around the dams? Hydropower is responsible for about 20% of the world's electricity. Dams will return on Modern Marvels. Today, the Columbia River is a vital shipping route, flowing from the Canadian Rockies in British Columbia through Washington and Oregon. Dams have made this possible, but only with some clever engineering.
The Columbia River is the United States' largest gateway for the export of wheat. About 8 to 10 million tons of cargo each year moves on the river. It's valued somewhere between $2 and $2.5 billion a year.
The dams on the Columbia River in Washington state, like Rock Island Dam and Grand Coulee Dam, don't have locks and don't allow ship passage. But just to their south, 8 dams, each with a lock, transform the Columbia and its tributary, the Snake River, into a water highway spanning 465 miles from the Pacific Ocean to Lewiston, Idaho.
Okay, starting to come ahead here in a minute.
A tug pushes 4 barges, each one the length of a football field, up the Columbia River towards the navigation lock at Bonneville Dam.
I'm going to open up the downstream gates, give the green light for them to come in. And at that point, he's almost dead stop. Otherwise, he would just ran right into the wall.
On dry land, you wouldn't want to negotiate a parking spot this tight.
650 feet is the largest tow you can put in, and you might have, a foot, 2 feet to spare on either end. So it's pretty tight.
It may be tight, but this lock is the only way to lift boats up 60 feet and over the dam.
Once I get the gates closed, I miter the gates, pushing them together, and then I start filling the water by operating 2 Tainer valves. Now these Tainer valves are valves that come open and lets the water come in, run in through the bottom, fill up the locks.
The lock is a glorified bathtub. You have a large empty structure. You have gates on either end. There are no pumps involved. This is all gravity.
But if it's a bathtub, it's a massive one. The lock at Bonneville Dam takes 10 minutes and needs a staggering 30 million gallons of water each time it fills.
Once it gets them up, I open the upstream gates, give them a horn, a green light, and verbally tell them they're cleared to go.
You'll see that agricultural and forestry products coming downstream, going upstream, fuel, fertilizers. The cost involved in that is so minimal compared to if you had to put them all on trains or if you had to put it all on trucks.
And you'd have to if it weren't for Bonneville Dam. Built over a 5-year period during the Great Depression, the dam deepened this rocky narrows, making it passable for shipping. Bonneville Dam is a concrete gravity dam that measures 180 feet thick at its base.
Size-wise, the 2 powerhouses are roughly 1/4 of a mile long apiece. The same thing with the spillway. We have a little less than 2 million cubic yards of concrete between the 3 structures. We generate about a little over 1,000 megawatts of power. The largest dam in the area, of course, is Grand Coulee. They produce 6 times what we have.
Completed in 1941, Grand Coulee is the largest concrete dam in the United States and typifies the multi-purpose role of the dams on the Columbia River. The dam is used for power production, flood control, and irrigation.
If you think of the Pacific Northwest as the states of Washington, Oregon, Idaho, and the western half of Montana, about 2/3 of the power that is consumed in those 4 states is produced by hydropower region-wide.
Though beneficial to people, the dams on the Columbia River are damaging some of the river's original inhabitants, fish and in particular, the region's salmon populations. Salmon hatch in the river, migrate to the ocean to mature, and return up the river to spawn. The dams present a huge obstacle to migration, particularly to the small juveniles, or fingerlings, heading out to sea.
At each dam, you have a very high percentage of juveniles dying, and it's additive. So if you're looking at 10 to 15% at each dam, you've already lost a really large chunk of your potential run size before it even goes to the ocean.
The natural tendency is, if you're generating power, is the water is in essence driving the fish down toward the turbines.
In an effort to reduce losses, the Army Corps of Engineers has installed a number of structures to protect fish, including fish screens.
Submerged traveling screens. They are large structures that slide down in the upstream side of the dam, and then they angle out, and then they have a motor on them. The fish come down, catch the current, and then they're directed into a bypass system. The bypass system simply is water flowing around the structure rather than through the structure, and then they're deposited downstream.
During this process of moving the fish around the dams, workers at the dams are able to collect about half of them, which are then loaded into barges and shipped downriver directly to the ocean. Barging reduces fish mortality at the dams, but trauma experienced en route may simply lead to a later death in the ocean. Adults returning to spawn can use man-made fish ladders to pass over the dam.
At each of the dams, there is a flow that comes through the ladders that attracts the fish. The fish then, in essence, are swimming through a small man-made stream, rising 2 or 3 feet at a time, moving up the 100-foot rise in most of the dams on the Columbia Snake system.
Fish ladder is a path that allows you to go around the dam. You get fish waiting down at the bottom for a chance to get up, and they're using up their energy there, and then they have 20 or 30 miles of slackwater lake to swim through.
When I first got to this project in the early 1980s, hydropower was king. If something interfered with hydropower, we didn't do it. Now, fish is king. And if it interferes with fish, we don't do it. If that means shutting off a powerhouse, that means shutting off a powerhouse.
But why has fish welfare become so important?
The main reason, of course, is the Endangered Species Act. That, of course, gives it a lot of clout. So with the runs getting dangerously low, every fish is important.
There is tremendous amount of effort going in on the part of the various agencies to make sure that fish can get up and down past these dams. But at the end of the day, we've got a lot of runs that are upstream of the dams that are not doing well, and there's problems with them.
But the big dams are probably here to stay. There's little debate that hydropower is far cleaner than electricity derived from fossil fuels. But when dams fail, whole communities can be wiped out. Who is looking after our aging inventory of dams? As many as 1 million adult salmon and steelhead and 50 million fingerlings pass through Bonneville Dam in an average year. Dams will return on Modern Marvels. Flood. It's one of nature's most potent destroyers of life and property. In an area of frequent flooding, one of a dam's key selling points is its ability to restrain an onslaught of water.
While we designed the dam to hold a certain amount of water, we also designed features into the dam that allow us to pass excess water around that dam. So a big part is understanding how large is the flood that we would have to handle through some sort of a spillway in order to safely pass that water around the dam during a storm event.
But there are rare times when the dam itself is the cause of the flood. At 10 a.m. on June 5th, 1976, workers in southeastern Idaho tried desperately to close an ever-widening fissure in the downstream face of the Teton Dam. But the growing hole consumed their bulldozers. At 11:57 a.m., the crest of the 305-foot earthen dam collapsed as its reservoir was being filled for the first time. 80 billion gallons of water crashed down on the farming communities below the dam. Directly downstream, 5 communities, Rexburg, Sugar City, Wilford, Salem, and Hibbard, were swept away. The wall of water ripped buildings from their foundations. 80% of Rexburg was inundated and damaged. The riverbank community of Sugar City virtually disappeared. The flood killed 11 people and 16,000 head of livestock and caused hundreds of millions of dollars in property damage. Loss of life would have been far greater had there not been time for an evacuation. The Teton Dam had been designed by the Bureau of Reclamation, a division of the Department of the Interior, now more than a century old. The Bureau oversees water development projects in the western United States and has built some 600 dams, including the Hoover and Grand Coulee. Teton's collapse marks the lone failure among the Bureau's major dams. It led to an investigation that revealed 3 main causes of the catastrophe.
There were open fissures in the foundation. Those conditions could have had more attention given to them during the design of the dam. There was a very challenging core material. The core material that was available locally was a silt material, which is highly erosive, and so it has to be very carefully protected. And really the third contributing factor was not having some defensive measures that we now use on a regular basis when we're designing embankment dams, namely being filters to keep the embankment materials where they belong. The Teton incident had an impact on the federal government, understanding that it had this tremendous infrastructure that needed to be cared for, it needed to be paid attention to.
Caring for aging western dams is one of the main missions of the Bureau of Reclamation's engineers at their Water Resources Research Laboratory in Denver, Colorado. At this massive facility, they test ways to mitigate the host of factors that can cause a dam to give way. Water is incredibly heavy. A single gallon weighs in at more than 8 pounds. Dams direct their reservoir loads into their foundations. The water exerts 17,000 pounds of pressure per square foot onto the base of a dam the size of Teton Dam.
You have to take a look at the potential weaknesses in that foundation that would allow some sort of slippage that would then allow a piece or all of the dam to slide downstream and release the reservoir. You may find that there are storms possible that were never envisioned by the original designers, which in that case would lead to an overtopping of the dam and erosion of the downstream face.
Overtopping, excess water spilling over the top of a dam, is the most common cause of dam collapse.
Spillways are really our primary feature for managing the release of water around a dam. In a flood event particularly, the spillway is basically a safe channel to carry the water around the dam and get it back into the water course downstream.
At their Denver facility, Bureau engineers are testing a fuse plug, an earthen gate designed to give way and allow water to pass in a flood.
The water normally doesn't go through this spillway unless there's a big flood, and when there is a big flood, each one of the individual embankments will wash away in a prescribed manner in order to open up that section of spillway.
One of the challenges with spillways is to be able to quickly develop large capacities for discharge, but yet still be able to store water. And one of the ways traditionally to do that has been gated spillways. But to build a large gated spillway is extremely expensive. Whereas if we could replace those gates with an embankment that we could predict exactly how it would overtop, how it would breach, and know exactly how it would perform, then we would have a much less expensive solution.
With 90% of its dams nearing the half-century mark, the Bureau of Reclamation tests the strength of the concrete in each dam every 10 or 15 years.
A good durable concrete will continue to strengthen as time goes on. In some instances, there are things like freezing and thawing or abrasion, and we need to look at those items and monitor them over time.
Concrete continues to slowly hydrate for years, absorbing water and forming crystal lattices that give it strength. Over a 50-year period, the concrete in a dam may become as much as 250% stronger.
The smaller cores we usually test in our 300,000-pound machine. In there today we have a core from our Upper Stillwater Dam, and this core was taken from our 15-year testing program. Right now it's about 20 years old. The point of the test is to test in compression until we find the ultimate compressive strength, until it fails, and that's the maximum load that we can get out of that concrete.
A compressive strength test will measure how much pressure it takes to crush this core.
This cylinder just broke at 7,000 psi, which is slightly higher than we were expecting, which shows us that it's continuing to gain strength over time.
Dam failures, while catastrophic, are also unparalleled learning opportunities.
We had a significant incident with Teton Dam. We feel like we've learned some tremendous lessons. And as a result of learning those lessons, we have been very active in trying to share those lessons with others, both throughout the United States and throughout the world, to try to further the cause of dam safety.
We can also learn a lot from nature's quintessential dam builders. Their efforts are responsible for fostering some of the most vital habitats on Earth. Bureau of Reclamation dams provide irrigation water for 140,000 farmers in the American West, who produce 60% of the nation's vegetables. Dams will return on Modern Marvels. Beaver dams can have a dramatic beneficial effect on their surroundings. In many ways, these rudimentary constructions, built to create ponds that protect beavers from predators, are ecologically far superior to their man-made counterparts. A beaver dam has a positive impact on the local ecosystem almost immediately.
They trap sediment over time. Then you've got vegetation that comes in, starts filling in. You've got a wetland, and you've got wetland plants, emergent vegetation, and that creates great habitat for a number of species.
Big dams often simply submerge riparian habitats, the lush life-sustaining areas beside rivers. Beaver dams have the opposite effect.
Some studies have shown something like 7 to 8 times as much riparian habitat as a result of the beaver dams coming in.
Unlike large dams, which often store seasonal spikes in water volume, beaver dams don't block flows that are vital to the river's ecology.
It's habitat creation during those high flows. When you actually have a river depositing organic matter, creating this variety of habitats, it opens up new habitat for all kinds of species to explore, not just fish.
When you take out the variation in a river's flow, the fish and the bugs, they start to fade away. They're not getting the temperature cues and the volume cues that they need to complete their life cycles.
Water held in a large dam's reservoir stratifies, altering the temperature and chemistry of the water in the river below.
The water in a natural river is highly oxygenated, and it's roiling around. And when that river is dammed, you're basically changing this highly oxygen water into a slack water lake where the oxygen levels on top are bound to be very low and probably lower underneath, which is fine for lake fish, but not for riverine species.
Some of these river fish, like salmon, are vital food sources for humans, and water conditions at dams contribute to their declining numbers. Today, U.S. salmon populations are a mere 6% of their historic levels. But there may be a technological solution to this oxygen-depleted water.
We've developed hollow turbine blades. Normal turbines are made of a big cast steel component and they're solid, but utilizing these hollow turbine blade designs, we're able to draw air into the turbine in a cloud of small bubbles. They pass oxygen from the air bubbles into the water and therefore increase the dissolved oxygen in the water downstream of the dam, and that's great for fish.
After centuries of building dams, some communities in the U.S. are looking to remove them as an option, particularly outdated ones.
Communities are really embracing that where it makes sense. Roughly 550 or so dams have been removed in the United States already, over 200 since 1999.
In the case of the Cascades Dam in Yosemite National Park, removal would mean returning a protected environment to a more wild state.
I'm standing here on the banks of the Merced River here in Yosemite National Park. We're about 3 miles downstream for Yosemite Valley and right at the former site of the Cascades Diversion Dam. This dam was built in the early 1900s to generate hydroelectric power for Yosemite Valley. When the dam was taken offline in 1985 and no longer produced power, the dam and its structures were obsolete, so we as the National Park Service decided to remove the dam.
Completed in 1917, the 184-foot-long timber crib dam was constructed of logs spiked together to form cribs that were filled with rocks. Sheathed with redwood boards and flanked by 30-foot-high concrete abutments, this rudimentary dam presented challenges to the planners of its removal.
There was a huge concern that we would remove the dam and there would be this huge washing of sediments downstream.
What had cost $200,000 to build would cost $2.8 million to demolish. After 3 years of planning, a crew of 30 working with a bulldozer and an excavator removed the dam in just 2 months, November and December of 2003. Workers diverted the river to one side, removed half the dam, and then rerouted the flow back and demolished the other side of the dam. Engineers had tested sediment levels and found them to be low, so sediment didn't wash down and choke the river, as they had feared. Workers used excess sediment to fill the hole where the dam had been. With the dam out of the way, the environmental team set about restoring the habitat to that of a free-flowing river.
We had a number of areas to look at. We had the channel itself that was going to be exposed. We had a floodplain, and then we had this bank. And each of them had their own unique issues. The channel itself is going to drop 12 feet. That means that the water table is going to drop 12 feet. The floodplain is going to expand, and that's a great opportunity for us because that's a very biologically rich area for plants and wildlife. Overall, we planted about 3,000 seedlings here on the floodplains, all wetland species from the area.